Now let's look at the contract monad. And it comes with four type parameters, W, S, E, and A. So as in all monads, the last one is always the result type. So the A is the overall result of the computation. I will get to all three of the others in due time, but I briefly want to go through them now, just to give you an idea what they're for. So the W is like in the writer example I gave you. So it allows a contract to write log messages of type W. So in our example of the writer, it was just list of strings, but here you can specify some W. And I did say log messages, but the purpose is not really logging. The purpose is to communicate between different contracts. So the written W is visible from the outside. So this is a way for a contract to pass information to other contracts or to the outside world. The S specifies the endpoints. So what endpoints are available in this contract. And the E is the type of error messages. So similar to our examples of maybe and either, in particular either, we looked at either string where we had string error messages, but here it's more general, so you can specify the type of error messages, and then you can throw exceptions and also catch them inside the contract monad. So let's do a first example. Let's call it my contract 1. And let's say we don't want to write any state, any log messages, so we can pick unit there. Now we also right now don't need any endpoints, and for that there is empty. So we can specify the empty type, and that means no endpoints available. For error messages, a popular choice is text, which is a much more efficient type than string for textual data. So when you are dealing with large amounts of text or text in general, then text is normally a better choice than string. And finally, I don't want an interesting result, so I can take unit there as well. And the very first thing we can do is simply log a message. And this is not to be confused with making use of this W feature. This is just really logging, as we have seen before. So for that I can use contract log info, and now I need a string, or more general, I can use anything that's serializable that has a to JSON instance. So let's say hello from the contract. And now the compiler is complaining, and it's complaining that it doesn't know what the type here of this little string is. Normally, as I explained before, in Haskell, if you have a string literal, it's a string. But I activated this overloaded strings extension, which, as I explained before, allows you to use literal strings for more general textual types, including text or byte string. So the compiler at this point doesn't know what type this is. Is it a string? Is it a text? Is it something else? And in order to disambiguate this, I also added this type applications extension, which allows me to specify for a polymorphic function like loginfo at which type it is used. So loginfo is polymorphic and takes arbitrary serializable types, but I now wanted to use at string. And the syntax that is enabled by type applications is like so. So I can use the @ symbol and then the type name. So that means use this loginfo for type string. And then it's clear to the compiler that this literal string is indeed a string. Okay, if I want to test it, I also need a trace. Let's call it my trace. So that's of type emulator trace unit. And all I want to do is activate the contract. So I can, as before, do that with activate contract wallet. And let's say wallet 1, my contract 1. And in order to test that, I'm using emulator trace IO again, my trace 1. So if I try this now in the REPL, I get an error because, you see here, couldn't match type contract handle unit empty text with unit. So the reason is I specified my emulator trace has return type unit, but as I explained before, activate contract wallet has return type a handle. It returns a handle to the contract. So if I want a unit result, I can, as before, use void to throw away the result. Now we can try this out. I must reload. And we see our log message here, hello from the contract. Maybe you're wondering why I qualified the log info with contract. The reason is that we can also log from the emulator trace monad, as I showed before, and the command is also called log info, but that lives in a different module in control monad freer extras. So in order to not confuse the compiler, I have to specify which version of log info I want. So I imported this qualified, so I can say contract if I want the log info from Plutus contract, and I can say extras if I want the log info from control monad freer extras. Next, let's try to throw an exception. And as I explained before, the third type argument, text in our case, denotes the type of error messages. So I can throw an exception where the error message is a text. So let's do that, and you throw an exception with throw error, and then as argument the error message. So let's say boom. As I mentioned before, I activated this overloaded strings extension. Therefore, I can give text as a literal string. If I try this, I get an ambiguity error. So that's the same issue as with the log info, that you can also throw exceptions in the emulator trace monad. So there are two throw errors in scope, one coming from Plutus contract, one coming from Plutus trace emulator. So I have to disambiguate this. So I want the contract one. If I try again. Now I just get a warning, do notation statement discarded a result of type any. Right, so if I want to avoid this, I can also use void to throw away the result. So now we shouldn't see this error anymore, and I can run it. And now we note the log message has disappeared, and instead we see this line where it says contract stopped with error, and we see the error message. And in particular, as I mentioned, the log message has disappeared, which is what you should expect of exceptions, that the execution of the contract stops at the point where the exception is thrown. So at line 21, execution of the contract stops and it never reaches line 22. This is the same behavior that we saw earlier with the maybe and the either string monads, where in the case of nothing or left, the rest of the computation didn't matter and was discarded. Next, I want to show how to catch or handle exceptions. So for that, let me just copy everything I have so far and rename it to 2. And the idea is now that in my contract 2, I want to basically run my contract 1, but I want to catch the exception. And let me change the type here. Let me change text to void. Now what is void? Void comes from data.void, and it's a type that has no values. So that's different to unit. Unit has exactly one value, which is also called unit. Void has no values. So what does it mean to have a contract that has this third type parameter, the void? Well, that means this contract can't possibly throw an exception, because in order to throw an exception, you would need to call throw error at some point and provide an error message of type void, but there is no element of type void, no value of type void, so you can't do that. So there can't be an exception. So this type signature of a contract would tell us that this contract can't possibly have an exception. So let me delete this. And what I want to use to handle the exception, it's also in contract, and it's called handle error. So let's try to understand the type. So it takes two arguments, a handler and a contract. So it takes a contract with error type E and result A handler from E to contract where the error type potentially can change to E prime, and the overall result is a contract where the error type is E prime. So how does this behave? It executes the second argument, this contract here, and if there's no exception, we get a result of type A, and that will be the overall result of this resulting contract. If, however, there is an exception of type E, then we apply our handler to it and get a contract with error type E prime, also result type A, and run that instead. So if I want to try this, I first need to provide the handler. I can do that as a lambda term. So this R is now of type text because the E in our case, because I want to apply this to contract 1, is text. And now I must provide a contract that can't throw an exception. So an example would be to simply log the error message. I could use log info again, but just for variety, let's use something else. Let's use log error. And I just want to say chord. And now I want to show this error message. Now the error message is not of type string, it's of type text. So in order to convert it to a string and then concatenate it with this chord literal string, I have to convert the text to a string, and there's a function to do that in data.text. It's called unpack. So I unpack error. Note that in this case I don't have to specify, like I did here, at which type I'm invoking this, because the compiler in this case can deduce the type, because it knows that unpack results in a string. So it takes the text, results in a string, and then I concatenate it, so this must also be a string. I'm using these overloaded strings, so the literal here by itself could also be text or byte string, but because I'm concatenating it with a string in order to be type correct, this chord also has to be a string, and then the concatenation is also a string. So the compiler knows, in this case, I want to log a string. Okay, and now the contract that I'm handling, so my contract 1. And that should work. Let's see. I'm reloading and running test 2. Let's check. And we see there is no error in this case. So we see contract instance stopped, no errors. And we do see the expected log message where we say chord boom. So what happened? This handle error will first try to run this contract 1, and this, as before, will raise this exception in line 21 with the error message boom. This will now be caught by the handle error, so the boom text will pass into this function as R, and then instead of throwing the exception, this log message chord boom will be logged. By the way, it would also have been possible to implement something like handle error in the maybe or the either string monads. I didn't do it there, but you can implement a function like that there as well, which might be a nice exercise for you if you want to play a bit with monads and these various types. One other thing I should mention in the context of exceptions is that there are other ways in which they can arise, not just by being explicitly thrown with throw error. So there are certain operations that you can do related to the blockchain that can result in exception. Of course, maybe internally in the implementation of those operations, throw error is used, but that's opaque to the user. So for example, if you try to submit a transaction, that can fail and result in an exception. And the reason is that something can be wrong in the way you constructed the transaction. So for example, the way it works in Plutus off-chain code is you don't directly give the transaction. Instead, you specify certain properties that the transaction should have. For example, you can say this transaction should pay 100 ADA to that address. And then the algorithm will try to construct a transaction with this property. So in particular, in this example, it will look at the UTXOs that belong to you, that are in your wallet, and find enough inputs to cover these 100 ADA plus fees. And if your wallet doesn't contain enough funds to pay 100 ADA to that address, then that step will fail. And then when you try to submit the transaction, you will get an exception. Next, let's talk about the second type parameter, the S, which defines the so-called schema, which means the endpoints, the available endpoints that you can invoke from the outside and put data into the contract from the outside. Let's start a third example, my contract 3. Okay, again, we don't use the first parameter. Now we are talking about this one. Then let's use text error messages again and no interesting result type. So how do we specify the schema? Normally, you don't have to, you could just write that directly here, but normally one defines a type synonym and the name of the type contains the word schema, but that's just a convention. You call it whatever you like. And let's say we want an endpoint that's called foo of type int. So this is now like a quite advanced Haskell feature. This is not a normal value level string, it's a type. It's a so-called type level string. So this whole thing is a type. This my schema is a type. And so like int, this foo is also a type. And this is made possible by this data kinds extension that I enabled. Okay, so and now I can use this my schema here as second argument. As I said, I could just as well have written endpoint foo int here directly. But if this gets more complicated, then it's normally better to define a type synonym. So now how do I work with this? So there is the endpoint function. And if we ask for the type of endpoint, then it looks extremely complicated. But we can ignore most of that. The interesting part is this argument and the return type. First of all, here this known symbol L, that is the type level string. So in foo in our case. And this endpoint value A, that's the int in our case. So the L is foo and the A is int. So first of all, what is this promise thing? That is basically, as you see, it has also these 4 type parameters, same as contract. So this is a contract that's blocked or waiting to be triggered by an outside stimulus. So promise is like a contract waiting to get started. So that's the result of this thing. And what's this argument? Well, it is a function that takes an A, which is this value of the endpoint, so int in our case, and turns this A into a contract WSAB. So the behavior of this would be when we reach this endpoint function, we wait, we block until somebody calls the endpoint from the outside and provides an integer, because a is int in our case. And once we have an integer, we apply this function to it and get the contract and run that contract. But the whole thing is a promise. So let's do this first. So endpoint. Now I also have to help the compiler and tell it which endpoint. So because this is a type level string, I can't just use it as a normal argument. It's not a normal argument. It's again done via this type application. Okay, and now I need this function from int to contract. And a possible function from int to contract is our log info again. So the log messages can be any type that's serializable to JSON. So int is an example of that. So given an int, I can apply log info to that int and get a contract that logs that int. Now, like this, that wouldn't be type correct because, as we saw, endpoint is a promise and not a contract, but I'm defining a contract here. Luckily, there's a way to turn a promise into a contract, and that's called a await promise. So actually, I don't need this do here if it's the only thing I do. So this whole construct, what will it do? So this await promise, it will wait, it will block until this endpoint is called with an int. And once this int is available, the contract will continue with this. So it will apply this function here to the provided int. So how do we test it? So we also need a trace. Now let me also introduce a do block here. So first we have to start the contract again. But now that is not enough, because if we just started, it would just wait forever at this point until this endpoint is called. So we want to call the endpoint from our emulator trace. In order to do that, we need the handle. So until now, we have always used void to throw away the handle that this activate contract wallet returns. Now we can't do that anymore. We actually need it. So let's bind to it. So now we have bound our handle to H. And now we can use call endpoint from the emulator trace monad. We check the type of that. Import Plutus trace emulator. Again, a very intimidating type, but in principle, it just takes a contract handle and EP, which is the value that we want to provide to the endpoint, and then it invokes this endpoint. And we also have to somehow tell the compiler which endpoint we want to call. So we need the handle and the value. First, I need to specify which endpoint to call. So again, with this type application and the type level string that is the name of the endpoint, foo in our example. And now I must provide the value that's then supposed to be passed into the contract. So it must be an int, so I can use 42. And I mustn't forget to specify the handle as well. Let's try it. Use test3. See, so the contract is started here, and then it would block until the endpoint is called, but we immediately call it. So here we see received endpoint call on endpoint foo. We also see the value, our 42, in this case encoded as JSON. And then the contract continues and indeed logs the number it received, as we said, because we used log info there. And then the contract stops without error. Now, what if we want more than one endpoint? In that case, we can make this my schema type more complicated. And there's a so-called type operator that is defined in the Plutus libraries, // So type operator is just a type constructor like maybe or list or either that's in this operator form. So, and in order to do that, you need yet another extension, this type operators extension. So that's why I needed that. And now we can define another endpoint. Let's say bar of type string, for example. And if I want to call that as well, now I do need the do block because now I want to also call the second endpoint. So I can just copy paste this and do bar here, for example. So in this case, in the first case, this endpoint expects an int and then locks it, and here it expects a string and then locks it. So if I also want to extend the trace to also call the second endpoint, I can do this. I don't need to activate the contract again, it's still running. So I can simply immediately call the second endpoint and now provide the string. If I reload and run test3 again, then we see here was the first endpoint call foo with 42, and we see that here we get endpoint call bar with the string Haskell. And for some weird reason, the first lock is written like this, and the second one has these 3 stars and capitals. And I have no idea why that is. There shouldn't be any difference. But in any case, it works. So we have now a contract with 2 endpoints, and we can, from the outside, call both of them and then determine what happens once these values have been received, these endpoints have been called. Finally, let's look at an example where we make use of this first type parameter, the W. That can't be an arbitrary type, it must be an instance of class Monoid. This is a very important, very common class in Haskell, and it has mempty and mepend. Mempty is something like the neutral element, and mepend combines 2 elements of this type to a new element. The prime example of a monoid is lists, where mempty is the empty list and mepend is concatenation. So, for example, I can say mempty list of ints, that will be the empty list, and I can use mepend 1, 2, 3, 4, 5, 6, and it will combine them. But there are loads and loads of other instances of this monoid type, and we'll probably see other instances in this course. But for now, let's stick with lists. So let's define a fourth contract where we now use, for example, list of ints, which is a monoid, as the first argument. This time we don't need endpoints, so we can use the empty schema, can use text error messages, and no interesting result. Let's start with a weight of 10 slots. Now we want to make use of this writer feature, and you can do that with tell, like when I used this writer monad as an example for monad. And tell takes 1 argument, namely the state you want to write. So let's say we write the list that just contains a single argument 1. So I use void here again because this has a return type, namely the slot that we've reached, but I'm not interested in that. So let's wait for another 10 slots and do another tell. Let's tell the list that just contains 2, and thus wait for yet another 10 slots. Now we also want to trace and to test. Delete this here. So as before, we first have to start the contract. Now let's wait here in the emulator trace, but only for 5 slots at first. Okay, and now the way we can look up the state of a running contract is by using the function observe state or observable state. And as argument, that takes a handle. So the handle of the running contract whose state we want to observe. so H in our case. And we can bind the result. So the result should be the state of the contract at that point in time. So let's call that access. And in order to inspect it, let's log it. So extras log info show access. Now let's do this again, but this time let's wait 10 slots. Let's call the result of looking up the state wise and log that. And let's do the same thing final time, another 10 slot, look up the state, call it z's and log it. And if you think about the timing, so that should be interleaved. So after 5 slots, the first tail hasn't happened yet. Then the tail happens, then we observe the state again here. Then the second tail happens while we're waiting, and we observe the state of final time after the second tail, but while this contract is still waiting the final 10 slots. Let's try it. Okay, the first observable state was around slot 5 or in slot 5. And here we get a log in slot 7. So it seems this takes some time, actually getting the state. And we see at this point the state is the empty list, because we looked up the state before the first tail happened, and at that point the value of the state is empty for the corresponding monoid. So in our case the monoid is the monoid of lists of ints, and the empty of that, as we saw before, is the empty list. So we get the empty list. So let's see. Here in slot 17 we get sent some state, and then here we log it in slot 17. So now recall the first tail was the list just containing the 1, and that's the state we observe at that point. Now somewhere here around 20 the second tail happens, and we observe it here somewhere, slot 27. And now the state is the list containing 1 and 2. So remember, the first tail was the list just containing 1, the second tail was the list just containing 2, but now the state we observe at this point is the concatenation of the two tails. Similar or exactly the same actually as in our writer example in the beginning when I talked about monads. So the behavior is that the state is this monoid. It starts with empty, and then each time we do a tell, mappend is used to update the state. So what we tell is mappended to the existing state. And recall that even though it's the behavior of a writer monad, which often is used for something like logging, the purpose, the intent of using this mechanism in the contract monad is not logging. For logging we have, as we have seen, other functions available, log info, log error, and so on. Instead, the intent for this feature is to communicate information to the outside. So if you have a long-running contract that wants to return results or report intermediate results or state, then using this tell mechanism, the current state can be observed from the outside. So in our case, the outside is our emulator trace, but in a real deployment, if you actually deploy a contract, run a contract on the real blockchain, then the outside would be the user, or rather the user interface, for example the browser. So if you have a UI to interact with your D app, then you can interact with a running contract in the one direction by invoking endpoints, and then the contract can communicate information back using this tell mechanism.